So good morning everybody, welcome back to the next week of KDD2. Finally we got rid of Lecture 2, High Dimensional Data. We finished that last week. So this week we will start off with a new lecture on a new topic on data streams. So we'll have a look at mining data streams, and this is the table of contents coming up for the next 2 weeks. We'll today focus on the introduction part and on clustering in data streams, and next week we will have a look on classification in data streams. So for the introduction, first of all I would like to set the limits of our lecture actually. So this is a kind of disclaimer because data streams are really challenging source of data, and typically if you want to process data streams, particularly analyze data streams, you have to address a lot of aspects from the hardware, from the processing environment, like what kind of operating system you're running your processings on, what kind of programming language you want to use. Is there a programming language which is more dedicated to the processing of data streams and stuff like that? The programming schema also. For example, MapReduce, which is a functional programming schema, also works quite good on data streams if you just adjust it a little bit and stuff like that. And of course also the algorithmic design. So how are the algorithms designed? Are they designed to run on a data stream, or more on a so-called batch scenario, which is the opposite of a data stream? So there are a lot of aspects you have to address actually, you have to take care of, and this lecture more or less only focus on the algorithmic design aspects, so that the data mining algorithms can process data streams. And we will see that this is by itself not so easy, but that is the sole focus of this lecture here. If you are interested in something more on the hardware or the processing environment side, you could also attend lecture Big Data Management, which focuses on other aspects here, especially on programming schemes and so on and so on. Also sometimes a little bit on hardware. So anyway, so in this lecture we will focus on the algorithmic design of data mining algorithms, specifically data mining algorithms, of course, so that they can really process data streams. So why is that challenging, or why is that a topic at all? Well, most of the data mining algorithms we got to know so far typically focus on the batch learning scenario. So the batch learning scenario does not have any kind of streaming approach. The complete data set, training set, is typically available to the learning algorithm in the batch scenario. So you can always access the whole training set or the whole data set multiple times if you want. So data instances can be accessed multiple times. For example, in clustering, we'll have an example of k-means on the next slide, but without an example here, DB-scan. So you typically compute during cluster expansion all those range queries, and you have to access for each range query, you have to access the whole data set. And you do that multiple times, obviously. For each point you compute the range queries. And for classifications, we also will have an example on decision trees, but also naive Bayes. In order to compute all those probabilities, you have to access the training data multiple times. So the implicit assumption here is, since you somehow access that data multiple times, you somehow assume that that the data is stationary. It doesn't change, which is quite the opposite if you are talking about streams, obviously. So in batch learning, you assume that data is stationary. It's not evolving. It's not changing. So you implicitly assume that the instances are generated by some stationary generating process, or if you deal with a mixture of processes, it's more than one, of course. Yeah. So if you look for clusters, for example, you typically assume that you have more than one generating processes, more than one generating process. Each of these processes obviously are assumed to be a cluster. So anyway, you assume that those generating processes, be it one or several processes, this process or those processes are not evolving, they are stationary. Yeah? And the same holds true for the patterns. Yeah, so the data is not volatile, the data is not changing, and that means also that the patterns are not changing. So that means one run, be it a little bit more complex, and of course it takes some time, and you may access the data multiple times, but after one run you have the patterns, and the patterns are the final truth, so to say. Yeah. So because the patterns are not changing, why is that? Because the data is not changing. So if the data is not changing, the patterns that you came up with are also not changing. So that is the implicit, or those are the implicit assumptions for batch learning, obviously. And here are the examples for batch learning for k-means, that we see that k-means needs full access to the data in each iteration, because, well, you know that you start off with some random models, and then you assign each point to the cluster representatives, then update the cluster models, the cluster representatives, reassign the points, update the cluster representatives again, reassign the points, and so on and so on. And every time you reassign the points, you have to access all the data points. Yeah. So in each iteration, you need full access to the data in the classical k-means or the classical k-means-like algorithms. And that is obviously not so easy for streams, as data is arriving probably. I mean, we haven't talked about streams, what are the characteristics of the streams, but we'll see that if the data is arriving potentially in a very fast pace, then you cannot afford to access the full data set multiple times. Especially the full history of the data multiple times, but we will talk about that right in a minute. So here is the example for the decision tree batch classification. So decision trees, as you may remember, are constructed top down in a divide and conquer manner, recursively. So they start off with a root of the decision tree, where you split the data according to the best attribute. So at the start, all the training examples are at the root node. You select the best attribute for the root, and then for each possible value of the test attribute, a descendant of the root node is created. So if you have two, for example, here a binary valued attribute, you get two descendants, two subtrees, and for all of those subtrees, you repeat the splitting of the attribute decision. Obviously at each level of the tree you need the full access to the full data set. Yeah, so for the root node you do the root splitting, of course, on the full data set, and then all data points or data objects that have this value in the first attribute go to this node, and the rest goes to this node. So you have a split of the training data, but in the end, for splitting those two nodes, so for splitting one specific level in the tree, you need full access to the entire data set. Yeah? Same like k-means. And that's why it is a typical batch classification model.